In the last video, we looked at the relationship between the phasor voltage and a phasor current when uh, they are applied to a resistor. Let's look at a similar excitation for an inductor and see how we get on. Okay, so we know the voltage and the current relationships in through an inductor. Voltage is given as L di over dt, and let's say our voltage is defined by this complex exponential and the current by this complex exponential. And let's now put it in this equation, right? So the complex exponential voltage is equal to L di over dt, and I is given by this complex exponential. If we resolve this equation, what do we get? If we differentiate this, we get j omega L Im e to the power j omega t plus phi. Now, if you use this expression and this expression and cancel the omega t or e to the power j omega t terms, what you are left with is this, right? And you could write this is, so here you have a voltage, the phasor voltage, and you have the phasor current, and you can write it in the polar form like this. And therefore, the relationship becomes V is equal to j omega Li. The relationship between the phasor voltage and the phasor current is the same as the relationship between the phasor between the voltage and current in the frequency domain. Okay, so let me kind of summarize. So in the time domain, you have the relationship between the voltage and the current is given by V equal to L di over dt. But in the phasor domain, which is also the frequency domain, but let's not go there. The phasor voltage is given as j omega L I, okay, where I and V are phasors.